Imagine looking into the universe and discovering a pattern hidden inside ancient light, something subtle enough to escape ordinary observation, yet strange enough to make astronomers stop and investigate. That is the kind of mystery that makes the James Webb Space Telescope so fascinating. Webb was built to observe some of the earliest galaxies in cosmic history. Because light takes time to travel, looking farther into space also means looking farther into the past. Ancient infrared light can therefore reveal conditions that existed billions of years ago. One particularly interesting target is the galaxy cluster Abell 2744. This enormous cluster contains so much matter that its gravity bends and magnifies light passing behind it. The effect, known as gravitational lensing, can stretch distant galaxies into arcs and make otherwise faint objects easier to observe. When Webb examined this region, it revealed an extraordinary landscape of distant galaxies and gravitationally distorted light. But the real scientific challenge begins when astronomers analyze the data rather than simply looking at the images. Light carries information. Its wavelength, intensity, polarization, and spectrum can reveal the physical conditions of the objects that produced it and the material through which it traveled. So when researchers encounter an unusual pattern, the first question is not whether reality has been broken. The first question is much simpler. Could something ordinary explain it? Astronomers must consider instrumental effects, calibration problems, background sources, gravitational lensing, dust, and limitations in the models used to interpret observations. This process is essential. A strange-looking signal does not automatically represent new physics. But unusual observations can still be extremely valuable because they force scientists to investigate their assumptions. One of the most fascinating possibilities explored in theoretical physics involves dimensions beyond the three spatial dimensions we experience every day. Certain theories, including versions of string theory, propose additional dimensions that could exist on scales far too small for us to observe directly. These ideas are mathematically sophisticated, but they remain theoretical. There is currently no established observation from Webb proving that an additional dimension has been detected. Still, the concept provides an intriguing way to think about unexplained phenomena. Imagine living on a two-dimensional sheet. If something from a third dimension interacted with that sheet, inhabitants confined to the surface might observe effects without being able to directly see the source. They would only see distortions. The analogy is imperfect, but it illustrates why physicists sometimes consider whether hidden degrees of freedom could leave indirect signatures in observable measurements. However, there is a major difference between a theoretical possibility and an astronomical discovery. For an observation to become evidence for new physics, it must survive repeated testing. Independent teams need to reproduce the result. Alternative explanations must be investigated. The instruments must be checked. The statistical significance must be established. And the phenomenon should ideally appear in independent observations. That is why an unexplained pattern is not the end of the scientific process. It is the beginning. If an unusual feature appeared repeatedly in Webb observations, researchers would compare it with observations from other telescopes and instruments. They would ask whether the same effect appears at different wavelengths. They would examine whether known astrophysical processes can produce it. And they would attempt to reproduce the observation using independent analysis techniques. Only after surviving these tests could the mystery become evidence for something genuinely new. And that possibility is what makes observations from Webb so exciting. The telescope is not simply taking beautiful pictures. It is testing our understanding of the universe. Every distant galaxy is another experiment. Every spectrum is another measurement. Every unexpected result is another opportunity to improve our models. Perhaps an apparent anomaly will eventually receive a completely conventional explanation. Or perhaps it will reveal a physical process that scientists had not previously understood. Either possibility would teach us something important. Because science advances not only when predictions are confirmed, but also when nature surprises us. And Webb is giving humanity an unprecedented opportunity to discover exactly how surprising the universe can be. The most fascinating mysteries in astronomy are rarely solved in a single observation. They develop slowly. A strange measurement appears. Scientists investigate it. Other researchers attempt to reproduce it. New observations are collected. And eventually, the evidence either becomes stronger, or the original mystery disappears. That is exactly how unusual observations should be treated. The idea that the universe might contain hidden dimensions is one of the more extraordinary possibilities considered by theoretical physics. Our everyday experience gives us three dimensions of space: length, width, and height. Physics also treats time as part of the structure of spacetime. But some advanced theories propose that additional dimensions could exist beyond what we directly experience. If such dimensions exist, they might be hidden at extremely small scales or otherwise inaccessible to ordinary observation. The crucial question is whether they could leave measurable effects. That is where the connection to astronomy becomes interesting. Gravity behaves differently from the other fundamental forces, and physicists have spent decades trying to understand why. We also know that our current theories are incomplete. General relativity provides an extraordinarily successful description of gravity and large-scale spacetime. Quantum mechanics successfully describes the microscopic world. But combining the two into a complete theory of quantum gravity remains one of the great challenges of modern physics. This is why observations of the distant universe matter. The cosmos provides natural laboratories at scales and energies that cannot easily be reproduced on Earth. Black holes, neutron stars, early galaxies, gravitational waves, and extreme cosmic environments all give scientists opportunities to test physical theories. Webb adds another powerful tool. Its infrared observations allow researchers to examine distant galaxies, ancient stars, dust, and the evolution of cosmic structures. Sometimes those observations reveal objects that behave differently from what earlier models predicted. That does not mean physics has failed. It means the models may need refinement. Astronomy has experienced this process many times. An unexpected observation can initially seem revolutionary, only for additional data to reveal a more ordinary explanation. That is why scientists are careful about extraordinary claims. If an alleged anomaly could be caused by calibration, data processing, gravitational lensing, or an unusual astrophysical source, those possibilities must be investigated first. The scientific method demands skepticism. But skepticism does not mean ignoring strange results. Quite the opposite. A genuine anomaly deserves intense attention. Researchers can examine the same data using different techniques. They can compare observations taken at different times. They can use different wavelengths. They can observe the same region with other instruments. And they can construct simulations to determine whether known physics can reproduce what the telescope sees. If every conventional explanation fails and independent observations continue showing the same phenomenon, then the situation becomes much more interesting. At that point, scientists may have evidence that an existing model is incomplete. But even then, the conclusion would not immediately be, another dimension has been discovered. There would still be multiple possible explanations. New astrophysical phenomena could exist. Our understanding of matter or gravity could require modification. Or an entirely new physical mechanism could be involved. That is the real excitement. Not knowing the answer. The James Webb Space Telescope has opened a window into an ancient universe that was previously difficult to observe directly. It is allowing scientists to study galaxies from eras when the universe was dramatically younger. It is revealing how quickly stars formed and how galaxies evolved. And every unexpected observation gives researchers another opportunity to test what they think they know. Maybe the universe is exactly as familiar physics predicts once we understand the observations correctly. Maybe there are hidden mechanisms waiting to be uncovered. And perhaps, someday, evidence will reveal that our current picture of reality is only one layer of a much larger structure. But that conclusion cannot be reached through speculation alone. It requires evidence. For now, the most responsible, and perhaps most exciting, answer is that the mystery remains open. Because the universe does not have to break the laws of physics to surprise us. Sometimes it simply shows us that we haven't discovered all of those laws yet. And that may be the most important lesson Webb continues to teach. The deeper humanity looks into space, the more we realize that understanding reality is not about reaching the end of the questions. It is about discovering better questions to ask next.